as we get close to Thanksgiving, it may be interesting to look at the case of how a scientist would cook a turkey. Now, we've always heard that cooking is an art, and frankly, I think I would agree with you. I mean, if we were to figure out how would we go about cooking a turkey, the first thing that we do is we don't go to our science textbooks. Anyway, where's the first place we go? We go to the internet, of course. So let's go to the internet and figure out a couple of things that may be important about cooking a turkey. So we can go to butterball.com, and they say, you know, if you would cook a turkey for at 325 for a certain amount of time, given different masses of turkeys, you'd have a well-done bird. Or we could go to Food Network. Food Network might be something that's useful as well, and we get data much like what we see here. Maybe we go to Epicurious. This was actually my first link in Google when I looked it up. And this doesn't look scientific at all. It's not even a continuous function. What happens if you have the wrong size bird and you're right in the gap? How are we supposed to figure out how to cook this thing? Or maybe we go to Taste of Home. That sounds like a delicious bird. Okay, that seems pretty reasonable. Or recipe tips. That's another place that we can look, right here. Now, none of these curves looks the same. So who's right? Who's wrong? I mean, cooking is clearly an art, because I look at these data all put together, it's clearly not a science. So how would a scientist go about cooking a turkey like this? Looking at different sorts of parameters to come up with the optimum way of cooking a turkey. And the way that a scientist would typically do this is through dimensional analysis. Dimensional analysis, you have to be kidding me. We've been carrying along with dimensional analysis all term, making sure that our expressions are in the right units, carrying around these units all the time. This is actually important? Well, it can be important. It turns out that this was really in favor back in the 80s more than anything else, which was before my time also, so I'm not that old yet. But I certainly knew about this from a lot of literature from the 80s, but this goes back a long ways. You can actually find a lot about a system by just knowing how the variables are going to work together in dimensional analysis. And say you have a certain number of variables that are associated with cooking a turkey, and those different variables have units associated with them. Maybe we could start to group things together in such a way that we don't even have to know the particular details of a turkey to know how to cook a turkey correctly. So let's say we wanted to have a perfectly cooked bird. And I know that perfectly cooked means that the interior temperature of the turkey is a certain temperature. Okay. Well, there are a couple of things that I would want to group together functionally in order to get that well-cooked bird. So we've got some weird function, and it's going to have some variables associated with it. One of the variables that I already know is going to be the oven temperature. So there's going to be a lot of parameters associated with my bird. So for example, there's going to be a mass of my bird. That's going to have a certain size. I'm going to cook it for a certain length of time. That's going to be important. Maybe I'm concerned with the thermal conductivity of turkey meat. So we've got a K value. Maybe I'm concerned with what's the heat capacity, or the specific heat more appropriately for turkey meat. So we've got a C value in there. We might also be concerned about the density. I mean, the density is also something that could be important. So if I look at an expression like this, there are some important variables here, like mass and time and thermal conductivity and specific heat and density. But if we know our oven temperature and we would like to get an internal temperature that is safe for us to eat, these two things are in the same units, which means that this function must be dimensionless. It must be dimensionless. And it has a lot of things in here. I mean, mass is in kilograms, time is in seconds, thermal conductivity is in watts per meter per Kelvin, specific heat is joules per kilogram per Kelvin, density is kilogram per meter cubed, and we have to group all of these things together to get something that is dimensionless. Given all of these variables, given all of these units, it's possible that there's a couple of ways to do this, except for the fact that it's not. There was a theory called Buckingham's pi theory. I'll link the video where I post this video, so it'll either be in the page where we're looking at this or in some other place associated with this video. But Buckingham's pi theorem. And Buckingham's pi theorem says, there's actually a lot of things that it says, but it's a very important theorem in dimensional analysis, which, like I said, was important back in the day. And what it essentially says, if you know the number of variables that are important in your problem, and you know the number of units that are associated with those variables, and by units I mean kilograms, seconds, SI units. The difference between those, not the absolute value, but the difference between these is going to be the number of ways that you can group these variables together to get something of a dimension that you care about. So maybe number of possibilities. And I spelled possibilities incorrectly, of course. Possibilities, sure. Okay. And so if I look at this kind of an expression, I know how many variables I have. I have 5. Now I also need to look at what kinds of units that we have at play. So let's just quick do an analysis here. I've got mass, and mass has units of kilogram. And I've got time. Time has units of seconds. And I have thermal conductivity. Thermal conductivity, if you look in the book, is going to have units of watts per meter per Kelvin. Maybe it's watts per meter per degree C, but those are the same thing. Maybe we have a specific heat. Specific heat is in joules per kilogram per degree C or per Kelvin. And finally, we have our density. Density is in units of kilogram per meter cubed. Now, some of these units are base SI units, like kilograms, seconds, Kelvin. But some of these are derived units, joules and watts. And so what makes these things up? Well, a watt is a joule per second, and a joule is a kilogram meters squared per second squared. So units of work, where force times distance, so kilogram meters per second squared times distance, that's work, or joules. So kilogram meters squared per second, which means that a watt is a kilogram meters squared per second cubed. We have a meter on the bottom here. We have a Kelvin on the bottom here. So this meter cancels with this meter, and units of thermal conductivity are kilogram meter per second cubed Kelvin. Okay? We could also look at the units of specific heat. A joule is a kilogram meter squared per second squared. Kilogram meter squared per second squared divided by kilogram divided by Kelvin. So now we have all of our important variables expressed in their appropriate SI base units. Kilograms, seconds, meters, Kelvin, everything here is in those things. So coming back to this expression, the number of units that we need, SI units that we need, is 4. Meaning that there is one possible way that I can group these variables together to make something that is dimensionless. Okay, so how would we go about doing this? So let's look at this function. We're going to have some function, and I'd like to look at the character of this function. This isn't exactly what it is. There could be other constants that are at play. But as far as the way these variables have to work together to make this kind of relationship, what would actually make sense for us? So first, we would look at this and say that the bigger the turkey, the less temperature we're going to have on the inside. So mass is going to be something that keeps the inside from getting hot very quickly. So mass is going to be something that's in the denominator. And time. The bigger the time, the hotter the internal temperature is going to be. So I think time is something that's going to be in the numerator of this expression. Thermal conductivity. Well, if turkey meat is a good conductor of heat, it's going to move the heat from the oven into the interior of the bird quicker. So I think thermal conductivity is something that's going to be in the numerator of this expression. Specific heat, the bigger the specific heat of an object, the more heat it takes for the temperature to change. So specific heat has to be something that's in the denominator. And finally, we look at the density of this thing. And density is also going to be sort of related to how much bird you have. It's not exactly the case, but I would guess that something that is more dense is going to be harder to push the energy into. So density is probably going to be something in the denominator as well. Now we have to figure out how these functions, how these variables can go together to make something that's dimensionless. So what we might say is, I don't know what the power of any of these things is, but let's just try to figure out what the power is. And I'll just say that I have my time to the alpha power, thermal conductivity to the beta power, mass to the gamma power, specific heat to the delta power, and density to the epsilon power. And if I group all of these things together, I have to get something that's dimensionless. So what is time? The units of time is seconds. The units of thermal conductivity are kilogram, meter, per second cubed, Kelvin. We're going to have this to the beta. We're going to have mass, which is kilogram, to the gamma power. We're going to have specific heat in meters squared per second squared Kelvin. And we're going to have density in kilogram per meter cubed. And this is a delta power, and this is an epsilon power. So we're grouping all of these things together to get something dimensionless. So if I look at my units of second in this expression, I have a second to the alpha power, I have a second to the minus 3 beta power, I have a second to the plus 2 delta power. That's all my seconds. Or maybe I want, what's next? Kilogram. Let's do kilogram next. Kilogram to the beta. Kilogram to the minus gamma. And kilogram to the epsilon. Minus epsilon. Kilogram to the minus epsilon. And I think that's all my kilograms. What's next? Let's do meters next. So we've got meters to the beta. We have meters to the minus 2 delta. And we have meters to the plus 3 epsilon. And finally, we have Kelvin. And looking at my expression, I have Kelvin to the minus beta. And I have Kelvin to the plus delta. So grouping these things together, I don't know what alpha, beta, gamma, delta, or epsilon are, but as far as putting this functional form together, grouping all of the units together, we are going to have seconds to this power, kilograms to this power, meters to this power, and Kelvin to this power. Except for the fact when I group all of these things together, I need something that's dimensionless. So in other words, what we have found is that alpha minus 3 beta plus 2 delta must be equal to 0. And we see that beta minus gamma minus epsilon must be equal to 0. And we see that beta minus 2 delta plus 3 epsilon, that must be equal to 0. Make sure that doesn't go to sleep. And we see that minus beta plus delta has to be equal to 0. So what we have here is 4 equations for 5 unknowns. We can't solve it uniquely, but we can solve all of these things in terms of one variable. And then once you put in some answer for that one variable, you figure out what all of the other 4 variables are going to be. So we're just solving a system of equations here. So let's start here with this expression. From this expression, I see that delta is going to be equal to beta. Whatever we pick for beta, delta is going to be the same thing. And now using this, I can go to this expression and find out what epsilon is. So we see here that 3 epsilon is going to be equal to 2 delta minus beta. And delta and beta are the same thing. 2 beta minus beta is just beta. So we see here that epsilon is going to be beta over 3. Okay, now I know epsilon and I know beta. I can get gamma in terms of beta as well. So gamma is going to be equal to beta minus epsilon, but epsilon is beta over 3. So gamma is going to be 2 beta over 3. And now up here, if I want to find alpha, alpha is equal to 3 beta minus 2 delta, which is 2 beta, which is equal to beta. So I've written all of the other variables in terms of beta. So why don't I just set beta equal to 1? Alpha could then be equal to 1. Beta is equal to 1. Gamma is equal to 2/3. Delta is equal to 1. And epsilon is 1/3. So I can group all of these things together and make something dimensionless if these powers are associated with this. So what we have now done is we wanted to come up with a dimensionless function. One way of making this dimensionless function is using this sort of technique. And so what we have now found is this sort of functional form has a 1 right here, has a 1 right here, has a 2/3 right here, has a 1 right here, and we have a 1/3 right here. So if this dimensionless function is constructed in this way, our internal turkey temperature is safe to eat given our basic oven temperature. Wow, that was a lot of stuff. Let's give ourselves a little bit more space over here again. And what we have found is that the internal safe cooking temperature associated with some given oven temperature is going to be some function that looks like time times thermal conductivity divided by mass to the 2/3 power, the specific heat to the first power, and density to the 1/3 power. And there might be some other constant in there. We'll worry about that later. But this is something that's going to be dimensionless the way that we want it to be. And our internal temperature of the turkey, 165 Fahrenheit, associated with an oven temperature of probably 325 Fahrenheit or so, this is going to be some small number. So I'm going to group all of this stuff together, and I look at this. For an appropriately cooked turkey, it took a certain amount of time for a given mass. Specific heat of turkey is specific heat of turkey. Thermal conductivity of turkey is probably thermal conductivity of turkey. Density of turkey is probably density of turkey. So all of these things are probably just kind of numbers. So let's create something called the turkey number. And the turkey number, a dimensionless turkey number associated with cooked turkey, I'm going to call it specific heat times density to the 1/3 power over time over thermal conductivity times mass to the 2/3 power. This is what I'm going to call the associated turkey number. This number is associated with any turkey that you want properly cooked. It will always be the same number. Now you think to yourself, I don't know the specific heat of turkey. I don't know the thermal conductivity of turkey. I don't know the density of turkey. I guess I could know how long I cook it, and I guess I could know what the mass of the turkey is, but this isn't terribly helpful yet. The important thing to note is that this is a number that's the same for any turkey that's properly cooked. So why don't we rearrange terms? What I'm really concerned with is how much time it takes to cook this. So let's just rearrange this. Specific heat, density to the 1/3 power, over some constant turkey number associated with properly cooked turkey. I come up with an expression that looks like this. All of these things are just some constant associated with turkeys. So why don't we call this the turkey constant? C sub t. Okay? So we've got our turkey constant, C sub t. And now, from knowing this turkey constant, you tell me how big your turkey is, and I'll tell you how long to cook it. All of the stuff in here, the specific heat of a turkey, is going to be true for every turkey. Density of turkey is going to be the same for every turkey. Thermal conductivity of turkey, it's going to be the same for every turkey. And the properly cooked turkey number is the same for every turkey, related with the ratio of the internal temperature to the oven temperature. This is all a constant. So now we have an expression. Time to cook a turkey is the turkey constant times mass to the 2/3 power. Okay. Now we need to figure out a little bit more data. Now we can go to the plot. Now, we actually look at a lot of this sort of data, and they don't agree. But you can guess that these chefs that go into the kitchen and try to make an appropriate bird are doing the best that they can. And the numbers that they have on these plots are representative of something that's fair, right? So let's say we go to some data here, and maybe for a 15 or 16 pound bird, it's going to take something like, 3.5 hours for an uncooked turkey. So what kind of numbers are we coming up with here? So it's going to be something like units of 3.5 hours, give or take, divided by a 16-pound bird or so. 16 to the 2/3 power I've got something like 0.55. So CT for a unstuffed bird is something like 0.55, give or take. What if we wanted a stuffed bird? Okay, so maybe that's going to be 4 hours for that same bird. So 4 divided by 16 to the 2/3 power. So we've got something like 0.63. Something like 0.63. And these have units. We should probably keep this in mind. This is, of course, mass is in kilograms, and it's not in pounds. But, you know, this is going to be representative. So there's a factor of g that's floating around somewhere that's just going to be constant. But let's just say we've got something like pounds per, it's going to be hours, sorry. Hours per pounds to the 2/3 power. And here this is 0.63 hours per pound to the 2/3 power. So this is just some turkey constant. Now you can use these numbers, apply it to your turkey. You multiply by this, okay, so there's, like I said, there's a factor of g floating around, but we're just going to use the data that they've already got on the plot. So there's a g, okay, that's fine. But you tell me how big your bird is in pounds. You multiply, you take that mass to the 2/3 power and multiply by 0.55 for an unstuffed bird, or 0.63 for a stuffed bird. That's how long you cook it. Now, does this make any sense? Okay, well, let's throw it up on a plot and see what we get. And I would say that my data here, my functional form, is very representative of what you might expect for properly cooking a bird. In the case of a stuffed bird or an unstuffed bird, it sort of plays right along with the data that you have. Now, before we continue on, I have to say that there are a number of internet resources, which of course must be trusted, that say that you shouldn't do this. It's really not safe because it's very unpredictable and could lead to food poisoning. So maybe the number that you need to keep in your mind is the turkey constant for an unstuffed bird, about 0.55 hours per pound to the 2/3 power. Happy Thanksgiving, everybody.